بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. So this is lecture 9 about named entity recognition. So far we have covered all the different type of NLP techniques, starting from recurrent neural network, transformer technologies, and in the previous lecture we introduced one of the most popular applications in deep learning, which is machine translation. And today also another very important application in natural language processing is about named entity recognition, which is basically transforming text into structured knowledge. And this means that we want to classify some words into entities. For example, trying to identify persons, organizations, locations, dates, or numerical expression into a particular sentence. This is the objective of named entity recognition. So why named entity recognition is important? First of all, as already introduced, it helps transforming an unstructured text, a long text, into knowledge. So what does it mean, knowledge here? It means that we can identify who did what and where. So who, it's basically the name of persons, okay, and did, it's actually the action that was taken, and what is this is, for example, could be where, it's a location. We can have also organizations, we can have numbers like financial data. So these are different type of knowledge that we can extract, and extracting this type of information, it helps enabling advanced search, because the search could be targeted into, for example, persons, into locations, into organizations, into named entities, instead of just searching a whole text completely unstructured. So using named entity recognition, it improves, help search engine to improve their indexing and identifying key entities that the users might search for it. Another thing is it can also help in supporting data privacy, especially in healthcare. We know that in healthcare, usually patient information or patient names is sensitive information. So having algorithms that automatically identify the name of persons can help to automate the way on how we can hide sensitive information like patient names in medical records. And also it powers data mining, because it helps extracting valuable entities like gene names or stock tickers from large text corpora for analysis. So this is a simple introduction and definition about named entity recognition, which is the process of identifying and categorizing the key informations, which we call entities in our case, inside a text, and classify them into predefined classes such as persons, organizations, locations, expression of times, or quantities, or monetary values, and so on. So you can see in this example, we have highlighted the name of the entities. We highlighted the name of Apple Inc. Okay, it's the name of an organization. London, it's the name of a location. And here we have a monetary value. Here we have an expression of the date, which is part of the time. This is the name of the person. And there are common entity types that we usually look for, but this is not restrictive. It can differ from one area to another. For example, in healthcare, we can try to identify special terminologies related to the healthcare sector. In the legal sector, we might try to also identify entities related to legal terminologies. So this categorization, it may differ from one sector to another. But the common ones are those that we have already introduced right now. Okay, there are different applications of named entity recognition. It can be used for information extraction, which is the objective of transforming an unstructured text to structured databases, which automatically populate the knowledge graph with entities and their relationship. And we talked about the search enhancement using indexing, so we can better understand the user intent by recognizing the entity in the query. Of course, this is in the era that is before Transformer and LLM-based chatbots. We don't need really this anymore in search, because now we use kind of semantic search with embedding. But before, things were completely different. So in order to improve the search, the knowledge of entities can help in the indexing and faster retrieval of the information. But now many of these technologies have dramatically changed with the Transformer. It can help also in the content recommendation, identify entities users engaged with the most. Okay, like for example, suggest new content containing similar or related entities, like for example, name of products that the user may be more engaged with. And also it has helped a lot in chatbots for matching the entities with the user intent and the potential answer of passages. So like machine translation, the name entity recognition has also gone through different stages. Of course, in early days, like in the 90s, there were also based on rule-based systems. Like machine translation, it was also based on rule-based systems. And here we can use linguistic patterns, using, for example, dictionary to record the name of the entities. For example, we can use a dictionary to record the name of the cities. We can have a dictionary to record the name of persons, and so on. Also, we can try to use regular expression to identify these named entities. And then after almost 10 years in the 2000s years, a statistical model has dramatic. So afterwards, statistical models have evolved through hidden Markov models. I'm going to introduce this today. And also conditional random fields, which basically use frequencies to learn probabilities, conditional probabilities, and then they can help to learn patterns from labeled training data. So it's kind of the early days of machine learning with manual feature extraction. And then with the deep learning and neural network, so using recurrent neural network and LSTM, it has evolved also from statistical models to deep learning models. So if you map this lecture with the previous lecture in machine translation, you can see that NLP fields went through the same stages, from rule-based to statistical models to neural network models, which we call deep learning, and now with the transformer models. And afterwards also, transformer models have been very effective using BERT architecture with an autoencoder to capture the rich contextual information and achieving state-of-the-art performance as compared to all previous models. So let's start with the first rule-based named entity recognition systems, which started back in the 90s and rely heavily on manually crafted rules and patterns. And these systems used at that time regular expressions to identify, for example, capitalized words. You know that the name of the persons or the name of the organization in English, they are always capitalized. So we can try to identify these capitalized words into a sentence to maximize the chance of identifying named entities. But of course, this is not very robust because the capitalization may differ from one language to another. But this can work for English and similar languages that could use capitalization. But capitalization, this is one of the patterns that we use. Okay, so we can use regular expression to identify potential entities based on capitalization or textual patterns. Another way is to use dictionary. So for example, we want to identify the name of cities. We can use a dictionary that contains the name of all cities, the name of all countries, or the name of all universities maybe. And this is what we call gazetteers, and which means the list of known entities to match the text against predefined lists of names, places, or organizations. Some others also apply contextual rules to try to also maximize the identification of named entities. Like for example, if we face the word Mr., So it's most likely that this is going to indicate a person afterwards. So the surrounding context is also an indicator or can give some clue to identify named entities into a sentence. And also for additional enhancement, we can also apply post-processing techniques which use rule-based corrections to refine entity boundaries and resolve ambiguities. Okay, so let's look at this simple example. We have an input text, and the objective is to find all the named entities using a rule-based approach. Mr. John Smith from Microsoft visited New York last Tuesday to meet with Dr. Sarah Johnson. Okay, so this should be our output, but to get this output, what is the strategy here? We're going to apply some predefined rules. Now we are still in the rule-based named entity in action. So we try to identify patterns based on capitalized words. Look, all these words are capitalized. So this will help to identify them and flag them as potential entities. So it's like shortlisting in the beginning. Capitalization can help making a short list. And then a second stage or a second rule that we can apply, we can have dictionary, for example, among all these words. We can try to check whether we can find them into a dictionary. Like New York, we can have a dictionary of locations, and we can have also another dictionary of organization. Or we can have also dictionaries like key value pairs. If I have Microsoft, this refers to an organization. If I have New York, this refers to a location. So that's a second stage that help identify with in finer grain details the category of the named entity. We can apply contextual rules. For example, if I find the word Mr., so I know that these words later that comes will refer to a person name. Okay, so this rule, the first rule, helps identifying the potential entities. Now I can say that John here, it will be mapped to a person entity because I have a Mr. just before this. Okay, and post-processing, like adjacent tokens like John and Smith are merged into a single person entity. I will not consider these as a person entity, these as another person entity, so I can merge them together. Like New York also combined, it refers to a single location. And this is a simple Python implementation using regular expression for identify potential entities using capitalization. So we can use regex. Okay, this is I think in JavaScript to identify capitalization, and here we apply the person rule. Now if I want to say whether from these entities, I can take the text and then we can try to identify this honorific, Mr., Mrs., or Dr., President. Okay, and based on this we can identify all the words, and then we will tag this word as a person. So the rules can go through different stages. Does it make sense? Okay. So the second approach is about statistical and feature-based models. And here there are different techniques because the rule-based are good but limited. You know, it's very difficult to generalize it to different languages, different contexts, and it doesn't capture all the richness of the linguistic patterns into a certain language. So the limitation of purely rule-based systems, it's evident, and the focus afterwards, starting from 2000, shifted towards machine learning techniques that helps to learn to recognize entities from annotated data. So it's basically a supervised learning strategy. And the most popular technique is the hidden Markov models and the conditional random fields. And I'm going to introduce in detail these two techniques. Also, decision trees were applied. It's used to derive features and make classification decision based on hierarchical rules. Support vector machine was also attempted. But the most popular ones, it's actually the hidden Markov models in the beginning, and then it was superseded by the conditional random fields, which is a discriminative probabilistic framework for sequence labeling that overcame the HAM limitation. Just to give you an intuition about the difference of both, you know that Markov chains are based on the previous state, on the history, to predict the next. So I have the current state, I know the knowledge of the previous state, and the memory can be one state before, two state before, and then I will try to make an inference about what could be in the future. So in the hidden Markov model, it's able to make a decision about the entity name based on the past, on the previous state only. So it doesn't capture very rich relationships into a long sentence, for example, or maybe the same name of the person can be repeated, but for hidden Markov models, because it has only a very short memory, it's not able to have an excellent matching of the named entities. And this was actually overcome by conditional random fields, which look at the sentence as a whole. So it has a richer contextual information as compared to hidden Markov chain, which only looks at the current word and the previous state. Okay, this is the main difference between both. So the mathematical foundation of statistical models are based on probability theory, the concept of sequence labeling, because we represent the text as sequences, and each token must be assigned to an optimal. So what is the objective? It's to assign every token to a certain entity tag, whether it is a person, whether it is location, or whether it is an organization or something else. Also, it's based on optimization algorithm like a gradient descent, especially in machine learning, trying to optimize the error or minimize the error, maximize the classification accuracy, and also vector representation to capture the semantic meaning. So let's look at this problem, the problem statement. So we can model in statistical approaches, we model the named entity recognition as a sequence labeling problem. For example, I take a sentence, okay, for example, this sentence, and we consider this sentence as what? This is the problem statement, a mathematical problem statement. We consider the sentence as a sequence of words. So this is a sequence of words that represent a sentence, which is modeled as x, x1, x2, until xn. We have n words, and they want to produce labels. So it's kind of classification problem, okay? Because the labels are limited. I can have 5 labels, 6 labels, 7 labels. So I want to map every word into a label. For example, this is a person, this is the person, this is a location, and so on. That's the problem. That's the problem. That's the problem how it is modeled. And the objective of named entity recognition is to find the labels y hat that maximizes the conditional probability, the label given the word. So x is the observation, it's the word, and y, it's the label. So I want to maximize the conditional probability that this label has the highest probability given this word. Okay, so now have x and y, but let's understand what is x and what is y. X, it's the observation, is what we observe, and y is what we want to predict. And in the context of hidden Markov models, we call it's the hidden state. Why? It's the hidden state because it's hidden. I don't know what. I don't know what is it in the beginning. I need to infer it. I need to predict it. And x is the observation, is what I'm able to observe, what I'm able to see. So what is the objective here? To find the list of labels that will maximize the conditional probability y given x, the label given assigned to this particular word. Okay, so we don't be afraid from the math. Math is just a way to represent a certain problem. Okay, and here, for example, we can have a list of tags which we call the IOB tag. Okay, tagging format. So B, it means the beginning of a named entity, and I, it means inside a named entity, and I'm going to show you the difference. And O it's outside of any named entity. It means it's not a named entity. And then you can have different categories or different entity types, like person, and this is denoted as PER. Organization is denoted as org, and location is denoted as loc, and date is denoted as, this is for temporal expression. So we can have B, PPR, it means the beginning of a person name, and IPER, it means, maybe the second word of a person name. And you apply everything for others. Because, any person, any organization, any location, or any entity, it can be composed of one word or maybe multiple words. This is why we have B for the beginning and I for the inside. And this is applied first to hidden Markov models. And hidden Markov models, they represent the joint probability, not the conditional here. So it's the probability of X and Y. The probability of all observation and the hidden state. We try to maximize it. And this is basically what? It's using the Bayes rule, it's the probability of a named entity given a previous one, because there is, in a sentence, there is a probability that you go from, for example, a person to a location, or a person to an object. And these probabilities are calculated based on a certain corpus. So we will see this in detail, so don't worry if you don't understand this equation for the moment. But this is what we call a transition probability, and this is what we call an emission probability. I'm going to explain this in detail with very simple and illustrative examples. And the objective here is to maximize this probability given the following inputs. So the second approach is based on identifying even a more rich information between the different words, or a better contextual relationship. And this comes in addition to what hidden Markov chain does. We try to define what we call an additional feature function, which try to provide some characteristics between the transition between a certain entity and another one. And this is what we call the conditional random field, CRF in short. And CRF can incorporate rich overlapping features without having any kind of independence inception, because hidden Markov chain, they consider that all the words are independent. Markov chain مبني على نظرية الindependence ما بين states. If we don't have independence ما بين states, there is no Markov chain. فأول assumption في Markov chain, all states are independent. لكن الحقيقة الكلمات, they are not completely independent. There is some relationship. So CRF comes to overcome this particular issue of the independence between the words and try to define a feature function that will govern the transition between any two states, hidden states. So it's a bit abstract now, but I provided clear examples. Let me just introduce the different techniques and then we dive deeper. And there is now the difference between HMM and CRF is the following. So hidden Markov models are simple probabilistic models. They are fast to train and decode, and they have well-established mathematical foundation. CRF, it has the same advantages but overcome the label bias problem because of it doesn't assume any kind of independence. It will use the rich contextual information, okay, to better identify features that will help providing a better labeling of each word based on also additional information. And CRF was considered as the state of the art before the beginning of the deep learning area, before starting with neural networks. So both models typically use the Viterbi algorithm to find the most likely sequence. argmax, Y star is the labels that will maximize the conditional probability. Okay, let's start now with the hidden Markov models. going to make a very simple example. Now, what is the objective here? The goal is that we want to find label or to label each word in a sentence. For example, I have John visited New York yesterday with a tag like person, location, and other. This is our problem. It's basically a classification. It's a text classification problem. But of course, at that time, we didn't have the same computing power, so neural network was not very popular. And they have recourse at techniques like hidden Markov model. So what is a hidden Markov model? It's a statistical model that helps, in the particular of name entity recognition, it helps label words in the text. And you can think about it as like someone guessing based on the current state. It's basically the best guess. So when the best guess is the guess with the highest probability, because all the objective is try to maximize the probability. So it's going to be a guess. There is a certain chance of making errors, but we try to minimize this error, okay, using some kind of statistical analysis of the text, of the corpus. So it can directly see whether a word is a person or location, but try to make inference or a guess based on previous guesses. لأنه it will make an assumption أنه what comes next will depend on the previous states. واضحة. So this is why hidden Markov models, hidden Markov chain, كلهم they have this kind of dependency on the previous state. So the previous guess, which is the transition probability, now I'm going to introduce that, is what label usually comes after the current one. مثلا إذا عندي person, what would be the label afterwards? Is it likely to be an object, or likely to be a location, or likely to be an organization? مثلا صعب أن نلقى person then organization. ممكن مثلا نلقى person بعد verb مثلا. Okay. من أين نجيب الخصائص هذه؟ من corpus, statistical analysis of a corpus. Okay. And it must be labeled, okay, to identify these type of patterns. In the beginning, and ممكن if you have the name of the person, if the name of the person is composed of two words, there is also a likelihood that another name of person will come afterward, which is the beginning person and the inside person classification. And also it's based on the second thing, how likely the word fits a label. Okay, a word مثلا لو ناخذ مثلا محمد, how likely Muhammad is going to be classified as a person. في بعض الكلمات لو محمد مثلا واضح، اما لو ناخذ بنك يمكن تعني بنك مثلا، او تعني مجلس على الرصيف او شيء مثل هذا. ف we will assign what we call a probability for every word to match a certain label, a certain tag. لأنه بعض الكلمات من الكوربوس يمكن يكون عندها different situations. بعض الأحيان تكون اسم شخص، بعض الأحيان تكون اسم organization. فورد مثلا اسم organization تاع سيارات، لكن هي اسم أشخاص في الأصل اسم شخص. أوكي، فبعض الأحيان يكون different type of probabilities. There is kind of uncertainty، لكن with the contextual information we will try to minimize the maximum likelihood of P of label given an observation. Okay, this is how it works. So this is the objective, is try to make the best guess based on the current and the previous state to identify the next hidden states. So now what I want you to learn is the transition probability, which is the probability to move from one hidden state to another, from person to organization, from person to location, from person to, I don't know, time or object. Okay, and also the emission probability, it means what is the probability that this word is actually a person or an organization or a location. واضحة. transition ما بين hidden states entities والemission mapping, classifying every word to an entity. It's really to understand this. فالآن given an input like this, our example sentence, John visited New York yesterday. Our goal is to correctly identify John as a person and New York as a location. So how this is done? It will be done step by step. So first of all, we will have tables which we call emission probabilities and transition probabilities, and assume that this table exists, and basically they are learned from a corpus, and I will talk about how we do construct these tables. But now, having our sentence, okay, John visited New York, so we will have an emission probability which assign every word to a certain entity. مثلا John, it has 0.1 or 10% to be a person, and 0.002 probability to be a location, and 0.001 to be outside, not an entity name. And using a greedy approach, I'm going to say, okay, the most likelihood that it's John would be a person. This is what we call the emission probability. Tells us how likely a word is, okay, a certain entity. Okay, John is very likely to be a person, the beginning of the person, but unlikely to be an non-entity. And visited is likely to be an outside of an entity, but it's likely, but not likely to be a person entity. So this is the emission probability. The transition probability, it's like this. What is the probability to move? Now, if I assume that John is a person, what is the highest probability? Next one. So there is a high probability that it could be next. If this is the beginning of a person, it's most likely that they will have an inside person just afterwards. Okay, and also 10% probability that it can be non-named entity like a verb. This is called transition. It's the transition from one state to another. Look, these are states and these are observations. And from observations, we want to go to the state. So basically, it's based on the Bayes theorem. Is it clear? Any question here? Okay, so emission probability, the probability to map a word into an entity, and the transition probability is the probability that the next entity given the current one. Okay. So if I say John, it's probability the beginning of a person name. If I say Smith, its probability is still the same person. And here, okay, if I say visited, so this is the probability is not part of an entity. This is the case of emission. Now, imagine that we have this. How to make inference now? The inference, it works with the Viterbi algorithm, and this is just a simple illustration how we can execute this step by step. Now, imagine that we have the following emission table, and the idea of the Viterbi algorithm is to try all paths through the state and keeping the best scoring one. الآن أول جملة إيش؟ John. مش ناخذ John, and then I'm going to investigate all possible states. John with person, with B person, or inside person, or with object, or with beginning of a location, or inside a location. The highest probability one is 0.1. So I'm going to consider this is that maximizes the current state. So I'm going to say John is a person. Now, the second one is visited. Now, from B person, we try to go to each other possible states. في الترانزيشن في الإيميشن أيضا. فنشوف الآن I will find that visited is mapped to O, which is outside, which is the best fit because visited is a verb and not part of the person name. And then we will do the same thing now, starting from O, which is the previous state. What is the most likely? Okay, the next state. We will try all the states, And we will find that the B log fits best because new often is the start of a location name. And this keep several iterations until at the end we come up with the best path through the sequence. This best path will not be obtained from the first time, but it can take several iterations until I find the set of labels that will maximize the probability of labels given observations, which is the product of the conditional probability of the transition probabilities with emission probabilities. واضح ولا؟ الإيكويشن هذه. And I have better equation in the textbook I've sent to you. Let me just show this. That's what we want to maximize. We want to find the list of labels y such that this product اللي هو transition probabilities نتاع كل الكلمات وال emission probabilities it's the maximum. طبعا there is a lot of combinations. We will try to find the best combination. So it's an optimization problem. And there are maybe different ways. Viterbi algorithm is one of the ways on how to decode. Okay. It can try several iterations until at the end we try to find the maximum. With the Viterbi, using the Viterbi algorithm, we will find the list of labels that will maximize this joint probability. Okay. So it's a lot of math, but basically it's about the intuition that we're talking about. And here it's without the math, and the Viterbi algorithm. So here, this is a simple example. You have an HAM might have learned that Mr., for example, given a name is high, okay, because it usually comes just before a named entity. And also through the large corpus, we are going to learn all these different probabilities, the transition probabilities between any two pair of words. Okay. And finally, we're going to have the final assignment with the traceback and the final tag. Every word will be assigned to a certain named entity recognition tag. Okay, now the question, how are emission and transition probabilities calculated from hidden Markov models? So basically, you need to have a supervised training approach. You need to have a labeled corpus. So there are data sets that will have several sentences, and these sentences will be tagged manually. And from there, we can do a learning, and here the learning is going to be through frequency counting. We're going to count. مثل ما كان أيضا statistical approaches في الماشين translation. كل statistical approaches مبنيين على Bayesian approaches والبايس theorem وكل, they're based on frequency counting and calculation of probabilities. This is how they learn. They will learn from the statistical patterns. And to calculate the emission and transition probability from a hidden Markov model, we need a labeled training corpus where each word has a known entity labeled O or person or location, like this. So why do we need this labeled data? The HMM need to learn patterns like John is likely to be a person, and the locations, for example, learning that New York is a location composed of two words, visited is not part of the entities, and so on. And this is how the learning works. So first of all, we're going to calculate the transition probability. So we will take every pair of words. Transition probability, we will take every pair of words and we will count TI, okay, given TG. So count the number of times tag TI follows the tag TG. The number of times person follows O. The number of times O follows a location. So from this labeled data, we are going to calculate the transition frequencies. How many times person has transitioned to O? how many times O has transitioned to B lock. Look now, I have one transition from person to O. I have a second transition from person to O. Here I have a third one. So all of these, we're going to count them all. And then I'm going to count the total number of the tag itself. مثلا نشوف هذا البرسن was repeated 3 times وكله after O. So I have 3 person tags and I have 3 transition person to O, so 100%. Now from this particular information I will say if I have a person tag, B person tag, the next one 100% will be O. But of course with the larger corpus we're going to have different patterns. So this is a pattern now. From this data set the pattern is 100% if I build on this data set. But of course the labeled data are going to be much larger. Like now the transition between O and block. Look, I have O and block. This is 1, this is 2, this is 3, but I have also from O to O, from O to O, and from O to person. So here I don't have 100%. So if I have O, I have a certain probability to make a transition to B lock. I have another probability to transit to another O, and I have also another probability to make a transition to person. So we calculate these transitions, like for example here, counting the transition between beginning of a person to inside person and beginning of a person to O. And based on a certain corpus, for example, let's assume that we have 100 tags of beginning of person. Among them, 80% they have transitioned to inside person, and 20% they have transitioned to outside of named entity. So now these are frequencies. These are the transition probability related to beginning person. This is how, and we will do the same for all the different labels. So if you have 5 labels, you will have 5 by 5 transition probability matrix. And you know, that's simple. Now I can calculate, this is a conditional probability. The probability that I have an I person given that the previous entity is B person is 80%. And the probability that the next entity is O given that the current entity is B person is 20%. Okay? And the objective is not always to choose after B person is an I person, but you know, the context that comes afterwards is going to make the adjustments of these probabilities to find the best mapping. Okay? So you need to compute the transition probability for every pair of tags into your set. This is the transition probability, and the emission probability, it counts how many times a token will result to emit, also a tag will emit a word. This is the emission probability, the mapping. For example, here I have John, and so this tag emits the word John. So given a data set, I'm going to calculate, for example, how many beginning person tags I do have. For example, 1,000. Among these 1,000, I have 100 cases that this beginning person is always John. So here I have 10%. The emission probability here, it's 10%. So it's basically a frequency calculation. So this informs us that when we see a B per tag, there is 10% chance the corresponding word is John. And you do the similar calculation for all other words that appear in the beginning person tag. Okay. So there is still a problem with this, is how to handle unseen data. Imagine that you have a corpus, but this corpus doesn't have all the information. For example, a word like anthropic doesn't appear, for example, into an organization tag. Let's say that this is like a new organization, and the emission probability of anthropic given org would be 0, of course, because it didn't learn this word during the training. So even 1-0 probability in a sequence make the entire sequence probability 0. الآن المشكلة we have a product of probabilities. يعني أي probability will be equal to 0, everything is going to be equal to 0. So this is going to be a big issue. So how to smooth that is to add 1. So the objective now is to make smoothing by adding 1, Laplace smoothing. It's the count plus 1. So now imagine that this is equal to 0. We're going to have 1 divided by the total number of words. So V is the size of the vocabulary, the total number of unique words. And here we add 1. So this is called Laplace smoothing. And now suppose that entropy never appeared in the organization. So without doing smoothing, we're going to have 0%, and this is going to induce all the probabilities to 0. The product of probabilities will be equal to 0. And with the Laplace smoothing, we're going to have a very small percentage, but still is not going to neutralize the product of the probabilities. Okay, and now entropy will have small but non-zero probability of being generated from an organization tag, which prevents the whole sequence probability from becoming 0. And this is the summary. This is what we need to calculate. We have emission and transition probabilities. This is how we calculate the transition probability between one tag to another. And this is how we calculate the emission probability that a tag corresponds to a certain word. And this heavily depends on the labeled data set. Okay. So the key takeaways here is that both emission and transition probabilities are calculated from frequencies in a labeled training data. This is stochastic approach or statistical approach. The transition probability model the tag sequence patterns, and the emission probability it will model which word belong to which entity types. And we can use smoothing techniques to handle ancillary word transitions to avoid zeroing the product of all probabilities. And these probabilities are the key parameter of the HMM, and they use the Viterbi algorithm to decode and find the most likely tag sequence. So this is all about the hidden Markov chain. Okay, let's just take a small break. Okay, so we have introduced the hidden Markov models for name entity recognition, and they provided an excellent contribution to this field, but still they have several limitations in the sense that they assume that there is an independence between the different states, and this actually has been overcome by the conditional random fields, which try to directly model the conditional probability. Now from a technical perspective, hidden Markov model try to maximize the joint probability P, X, and Y. And here the conditional random fields try to maximize the conditional probability P of an entity given a word, of a labeled sequence given the observation sequence, which is the sequence of words, overcoming many limitations of the HMM. So how does this work? It's basically the same problem. We have an observation sequence, which is the list of words, and we try to make inference about the hidden states or the labels of every word. But here, it's not like we are doing in hidden Markov models. We're not going to go in sequence one by one, but we will try to consider the whole context. It's like we will do a complete investigation before making any decision. And how this works? So basically we're going to take every word and we ask different type of questions, which we call a feature function. So a feature function is basically a question that we ask, and based on the response we can assign 0 if the response is no, and 1 if the response is yes. For example, I can take John and I ask, is this a person? So yeah, it's a person. So in this case, I'm going to assign a certain score for this particular function. There is a function related to person. There is a function related to capitalization. So we can think about different type of feature functions. And this will provide an additional context in addition to the sequential relationships between the different words and the different tags. So we can confidently label John as a person without looking at Smith, or York without seeing New. And this shows that sequence labeling is hard, and we need the context, we need the patterns, and we need rules. So the conditional random fields try to overcome the problem of giving a tag just based on the current state and the previous state, but we try to understand the whole context to be able to make the best inference possible. And this is an analogy if we think about HMM and CRF as two detectives try to identify crimes. Okay, let's see this analogy. Maybe it will give you a better understanding about the difference. So in the hidden Markov model, it's like the old school detective. When there is a crime, it tries to reconstruct the sequence step by step, how this crime has appeared. And it recreates how the sequence was generated by guessing the hidden path, okay, from the observations to produce that produced this current crime, okay, or the sequence of words. And this is, it's limited only, he can look at the current state based on, or can look at the future based on the current state and make a guess about that. And this is an analogy here. For example, the crime investigator tried to reconstruct what happened at the crime scene step by step. For example, first he say the penetrator entered through the door, then took the vase, and try to make sequence by sequence, because hidden Markov chain are going to process the words one after the other using the Viterbi algorithm until finding the sequence of tags that will maximize the joint probability. Now, for CRF or conditional random fields, it's like a modern judgment. It's like we use forensics. With forensics, that will try to capture as many arguments as possible, which we call clue, قرائن. Okay? So for example here, they can make DNA test, finger analysis, or several other tools. هذا كل نسميهم قرائن. بناء على القرائن هذا يتم اتخاذ قرار. Okay? This is what CRF tries to do. So they don't need to recreate the crime, but they took all the evidences together to make a judgment. And there is an evidence point, okay, that this person done something. So here now, to make analogy, we look at the whole sentence with all evidences. كل القرائن مثلا هل هذا person, هل هذا location, هل هذا, and then based on all the information collected, we try to find the best tag matching with these different words. So here we use all available information at once, incorporate hundreds of overlapping features, and consider a global picture before making a decision. And basically it's the same. We're gonna try to calculate the probabilities. Now let's look at potential feature functions. And the feature function design is an important part about the accuracy of the tagging or the name entity recognition process. For example, I have John, Google, New York. And what are the clues to help identify the name entities? For example, capitalization. This is a feature function, one of the feature functions that we can use. And all of them, all of these, they are all capitalized. But we don't know, now based on capitalization, we are not able to make 100% confirmation whether these entities are persons or are organizations or are locations. So it gives me some information, but it's not sufficient. Now let's try me investigate more. So I can have another one. Is it in the names list? So I can imagine that I have a dictionary. So it's like a combination of rules and statistics, both together, to try to maximize the chance of categorization, classification of these entities. And now, for example, I say, oh yeah, I find John in name list. I now have better discriminative approach. This is why CRF is called, it's a discriminative approach, okay? Because try to make discrimination with respect to what we call feature functions. But these features are handcrafted. Handcrafted. They are manual. A neural network, خلاص, you don't need to make this. It's made by neural networks. And a feature extractor and then classification. We do feature extraction and then we'll do classification. So this feature function is like manual feature extraction. And you are old school for machine learning. A neural network, when it came, it has removed the need for manual feature extraction to be fully identified. احنا لما نتكلم الآن في self attention, what did I say before? We try to extract different type of patterns. Maybe some of the patterns is capitalization. Some of the patterns, entities. Some of the patterns, gender. Some of the patterns, we don't know, locations or relationships. There are a lot of patterns into languages such that it's impossible to manually craft them. If it is possible to get all the patterns of the language manual, we don't need to have this neural network feature extraction. I want to link the dots together. This is like trying to identify feature function manually to make discrimination and try to identify the most likelihood. And now this is going to lead into 0 and 1's assignment or probability assignment that are going to be learned. And now I can Google New York. So all of these, they are not person. And then I can have clue the previous tag. So the previous tag is at, which is an O and in, at Google, in New York. And this can give more, at can give more intuition to an organization, and in can give maybe more intuition to a location and so on. And the next word is a Smith. Okay, the next word is, so these are different observations, different features that will give, it's like forensics, trying to identify any kind of clue, قرائن اللي تخليني نعمل القرار بطريقة أفضل. Okay. And based on this, we're going to assign weights. مش كل القرائن عندها نفس المصداقية. حتى الآن المحقق لما تجي القرائن يمكن شاهد عنده مصداقية أعلى من شاهد ثاني ولا قرينة أعلى. We need to make some weights. These weights are learnable من الcorpus. Okay. So here, for example, word is capitalized. I'm going to assign a weight of plus 2.3. Okay, it's a strong evidence for a named entity. And look, the word in names list هذه قرينة ثانية مش نعطيها weight أعلى لأن القرينة أقوى. يعني لما عندي اسم موجود في dictionary قرينة أقوى من الكابيتاليزيشن. الكابيتاليزيشن ممكن تكون اسم، ممكن تكون location، ممكن تكون organization. So these weights, of course, they are going to be learnable through, and then will be adjusted. ing form, okay, it takes -2, and at it takes +1, and so on. So we're going to assign some scores for the strong case of being the beginning of a person. And these weights, it's like the detective credibility. How reliable is this feature, okay, or this feature extractor? So you can think about all of these are kind of feature extractor for a particular type of entity category. And this is the mathematical formulation. Okay, it looks complicated, but we can understand it very easily. Now FG, which is in red, is the feature function, which we will design manually. And for example, it's القرينة اللي نحب نبحث عليها, capitalization, it's a feature function. So this is going to return a value between 0 and 1, usually. Okay, and lambda g, it's the weight that is going to be assigned to this feature function. حسب قوة القرينة. And this is learnable. And this zx, it's just a normalizer to make sure أنه كل probabilities هذا they sum up to 1. Normalization العادية. Okay, so it looks complicated, but you can think it very easily. There is an exponential here, but of course later on with the normalization all this probability will be equal to would be sum up to 1. Okay, so the final report is that CRF, it's like a team of detectives or feature extractors who submit a final report on how to label a sentence. فممكن تشوفوا المعاناة ما قبل النيورال نتورك. It was painful. I mean, this is not easy to think about what kind of linguistic patterns I need to identify to maximize the chance of getting into the best categorization. So the feature function are the individual's detective or feature extractors, the weight, how credible are these feature extractors, and the normalizer ensures that this probability makes mathematical sense and add up to 100%. And we combine all the weighted evidence and to pick the most likely explanation. What is our objective الآن? Is to maximize this probability. اللي تعطينا التاجز sequence of tags اللي تعطيني the highest probability هذيك اللي نختارها. Okay. And this is just another representation, same thing. This is our function. Okay. If, for example, I am here, it's a function, okay, that will take the current tag, the transition between two tags, and the observations all together. And this is, we will extract some feature from here. And here we will have the weight of the feature, and here we have a normalizer to make all probabilities adds to 1. Okay, بسم الله الرحمن الرحيم. الصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, let's continue talking about conditional fields, random fields, and this is a step-by-step illustration. And our problem is, as usual, we start with a sequence of observation, which are the words, like John works at Google, and the objective is to find the best match with their named entities using the conditional random fields approach. Okay, so the first step here is to define the feature functions, which we call the clues, al-qara'an. Okay, so at each position I of the observation, we use the features, which are our detective clues. And for example, the first feature, function f1, word is capitalized. That's a feature. Okay, for example, John is capitalized, so this will give us inference that this could be a named entity. Another possible feature is that the current word is in the name dictionary. Like, for example, John would return a yes, and we will see how we convert this into scores later. Another possible feature function is that the current tag in a person, beginning of a person, and the next tag is inside a person. And this will give us more evidence that this could be a name continuation, or it's a person name. Fourth possible feature vector is, for example, there is a current word is at. So this suggests the O tag, okay? Or maybe also a location tag. That could be a location tag as well. Okay, so the second step is to assign weight to these features. So we defined our feature functions, and then we assign the weight to the features. Each feature is assigned to a weight lambda that represent how important that feature is for making predictions. And these weights are learned during the training, and we use them here as an example. So for example, for F1 word is capitalized, we can assign, for example, a score of 2, because capitalization is a good indicator of named entity. For the second word, for the second feature function, the word in names dictionary, so we can assign a stronger weight because we have a stronger evidence. Being in the name list is a very strong evidence for the person entities. And we have a beginning person followed by an inside person. We can give a score or a weight because of 1, because this encourages multi-word person names. And at, we can give a negative score because the word at is unlikely to be part of an entity. So this is how we can assign scores, and these weights would be learned from the whole corpus, and the positive weight they indicate an increase the likelihood of a particular label when the feature is active, and the negative weight it decreases the likelihood of a label when the feature is active. And then the third step is to activate features for a label sequence. Now suppose that we try to label the sequence beginning person, O, and beginning organization. So we need to calculate these scores as the sums of lambda g and the feature function for a particular word. And for example, if we take the word John, so if we apply the first feature function f1, and so we can assign a score of 1 here because John is capitalized, and also John is part of the names that are stored in the dictionary. So here I can have 1 and 1. And in this case, I can have a partial score for John equal 1 multiplied by 2, which is the weight, the lambda, plus the weight lambda multiplied by 1 for the second in name dictionary. And these weights, we assume that they are calculated from our corpus. And then we take a second one, which is works. So works is not capitalized and is not in the name list. So the partial score is 0, which is likely to give it a label of O. Okay, so same thing here. At will be assigned to label of O because it has a negative partial score, and Google here it's capitalized, but it's not in the name dictionary, so it's going to have a partial score of 2, which could assign it more likely to this organization, beginning organization. Okay, and then we will add all the scores together, 5 plus 0 plus minus 1.5 plus 2. This will give us an unnormalized score of 5.5. Now the objective is to normalize it, to make it as a probability. You can think about like the softmax function. This is pretty much similar to what we know as the softmax function or the sigmoid, which converts the probability to 1. And this is going to give exponential 5.5 is 244, which is the unnormalized score for this sequence. And by dividing by the z function, which is the sum of all e scores. Okay, we make all the sums. So of course, the sum of all this probability will be equal to 1. So this is very similar to the softmax function for multi-label classification. Okay, and finally we select the best sequence. The CRF evaluates all possible tag sequences. It will explore all tag sequences, and then it will pick the one with the highest probability. فالفرق الآن, if we summarize الفرق ما بين الماركوف chain or الهيدن Markov model and CRF, so both they try to maximize a probability. The first one try to maximize a joint probability لأنه it assumes that there is an independence between X and Y. The second one doesn't assume the independence. It's based on feature functions. So it tried to maximize the conditional probability of Y given an observation X. And this is why it's much stronger than hidden Markov models. Okay, and this is a summary, visual summary about the different feature functions that we can have that will lead to different feature scores, and at the end we calculate the final probability. The next evolution, like we have seen also in machine translation, is the use of neural network. And neural network, they have the advantage of removing the need for manual feature extraction like we did here to extract the features using neurons. So this is the true transformation of named entity recognition with the rise of neural networks and deep learning, which significantly reduced the need for manual feature engineering. And also neural network, they have evolved from convolution neural network and word embeddings, bidirectional LSTM, in addition to CRF, and also transformer. Now transformer, of course, they have improved named entity recognition much more than any previous approach. So for BiLSTM-CRF architecture, it has been a staple for named entity recognition since 2010, of course with the start of neural network, combining the contextual power of bidirectional LSTM and the structured prediction capabilities. And there are different variations. There is a character level encoder, and the encoder here is to extract the features and to learn the character representations, capture morphological and orthographic features using CNN or LSTM over characters of each word. And the second approach is based on word level BiLSTM, which processes the sequence forward and backward to produce context-aware representation of each word. And there is another layer which applies also CRF layer. It adds transition scores and computes the best sequence of labels that maximizes the total score. So it's like here a combination of manual feature extraction and automated feature extraction. And dropout regularization, this is to optimize and reduce the overfitting like in any optimization problem. Okay, so here we do have two approaches, character level encoder and word level BiLSTM, which will be processed both in forward direction and in backward direction to have to capture both left and right context for each word, which is crucial for accurate entity recognition. It has also a global consistency because it ensures CRF ensures a valid label sequence and models the common transition between, for example, beginning of a person followed by the inside of a person. And it has achieved strong performance, 91% of F1 score classification on the English CONAL 2003 dataset with high result across many languages. And this is an illustration about the character level encoder and the word level BiLSTM. So what does this do? Actually, here it will look at how the word is spelled letter by letter. Okay, and because words like, for example, running, runner or run, they are related. So the LSTM will be able to learn the patterns from prefixes, suffixes, and capitalization. Okay, this is the kind of features that you cannot do manually. So it's much easier to learn through a neural network. So for example, this vector or this word will result into a small vector that encodes its spelling. And this will help the model understand the unknown and also the rare words. Another improvement is towards the word level context and using BiLSTM, so to read the sentence from the left to right and right to left to have a better understanding of the context of each word. Okay, so we have a forward LSTM sees what comes before, and the backward LSTM will see what comes after. And based on this combination, it will have a bidirectional understanding of the context. لأنه named entity recognition بعض الأحيان تحتاج تعرف الكلمة اللي تأتي من بعد before taking decision. So it's like enriching the context to have a global contextual understanding to be able to maximize the accuracy of the classification. Okay, so for example here, it helps understanding that apple is a company name and not a fruit. Now if I take Apple hired John, now if I take Apple only and I look only to this direction, so Apple most likely is the name of a fruit. But when I take it from the other direction, so when I say hired, now this will give me more the context of a company. And John is likely a person because it's hired, there is hired before. So bidirectional LSTM has made an important breakthrough in the downstream task of named entity recognition. And these are just a few more illustrations that I want to skip because I have another lecture about, it's a quick overview about chatbots I want to introduce. And at the end, we had transformers. We talked a lot about transformer, and one of the downstream tasks is the named entity recognition. Transformer have become the state of the art for NER, and they have used BERT approach, which is the bidirectional encoder representation, to improve the accuracy of named entity recognition. So we talked about BERT and language modeling using mask, and the objective of BERT is actually to find an embedding representation of the different words. And also we have the next sentence prediction. This is representational model, and this is generative model that we have talked about in the transformer lecture. And this is the classical transformer architecture for generative approach, for the representational approach, which basically is based on BERT. So the BERT will produce a contextualized word embedding that capture rich and synthetic semantic information. So using BERT approach, the embedding will be able to understand that New York is recognized as a location, because BERT has seen similar context during the pre-trained approach. The idea is to pre-train a model, and then we make a fine-tuning. Okay, fine-tuning, it's based on labeled data set using supervised fine-tuning to train a model to classify a sentence into different named entity recognition categories. Okay, for example, given this sentence, we can train a large language model like BERT to categorize, for example, Johnson with these probabilities, Google with these probabilities, New York with these probabilities, and so on. Okay, so a classification layer is added at the top of each token contextual representation. After creating the embedding, we're going to have a dense neural network to get with the softmax function to produce the classification. So it's just a classification problem with multi-label classification with the softmax function at the end of the contextual representation. So we will have a contextual representation, and at the end we're going to have a classification head that will be added on the top of the contextual representation to convert an input sentence into probabilities like this. And the transformer model that are very popular for named entity recognition, BERT, which is the original bidirectional transformer model that transformed NER performance, and it has reached a state-of-the-art F1 score of 92% as compared to BiLSTM, which reached 91%. And also Roberta, it's a robust optimization version of BERT with an improved training methodology. Okay, so this is just an illustration of BERT, the fine-tuning process. There is nothing new here. It's basically the same fine-tuning process that we have already introduced, but with more emphasis on named entity recognition.